I'd like to talk about a design tool known as Failure Modes and Effects Analysis, or FMEA. It's a design tool for assessing risk associated with the different ways or modes in which a part or system can fail. It identifies the effects of those failures and provides a structure for revising the design to mitigate risk where necessary. This tool is really useful for a lot of different things, and it doesn't have to be talking about catastrophic failure, things like the Tacoma Narrows Bridge, etc. It could be as simple a failure as, for example, a product doesn't appeal to a customer, or it doesn't give enough reliability that the customer likes the product. It's an inductive process. It's constantly asking the question, if this failure occurred, then what? What's next? And hashing out the consequences of those failure modes. It provides a method for quantitative analysis of risk. So we're going to be looking at the different failure modes and their different effects, and which failure modes and effects are most important to pay attention to is going to come out of the calculation. This is really useful for comparing design concepts or refining designs. So you can assess the risk in this type of design concept, and you can assess the risk in this type of design concept. And like a decision matrix or other such tools, it gives you kind of an ability to weigh one option versus another and further refine your designs and combine good designs and the good aspects of designs that make your risk low. It also gives a really good way to document safety review in an easy to read format. So it's going to be a specific layout that allows somebody later to come back and review your work and continue to refine that design. So there are 9 steps involved in this process. First, we're going to identify modes of failure, and these are kind of top level understandings of what a failure would be. So the car won't stop, for example. We're not going to go down to the level of detail saying that the brakes wore out or that the brake line burst and you don't have brake pressure, etc. We want kind of a top-level failure because we're going to be looking at the different effects of this failure as well as the different ways in which that failure can happen. Those are called failure mechanisms. So we're going to first identify the consequences in related systems for each mode. So for the example given before, the car won't stop. Consequences of the car not stopping could cause an accident, could cause you to speed, could cause a number of different things. And so these are consequences of this failure mode. Then we're going to rate the severity of each effect. So we're going to look at, okay, causes an accident. That's an extremely severe effect. That would be a 10. These are all on a 1 to 10 scale, where 10 is the worst, 1 is the best. So the severity, S, of each effect gets a rating. Then we identify potential root causes for each failure mode. So we're going to go back to the failure mode and say, okay, for this failure mode, the car won't stop. What could cause the car not to stop? The user doesn't hit the brakes fast enough. The user was driving too fast and couldn't stop in time. The braking system didn't work. The wheels slipped, etc. So there are a lot of different possible root causes, usually narrowed down to the point of what we call a failure mechanism. Things like corrosion, things like fatigue, that type of thing. We're going to identify those potential root causes, and then we're going to rate the probability of occurrence, again 1 to 10, for each root cause, where a 1 is not very probable that it will happen, and a 10 is guaranteed to happen at some point over the life of the component. So we're going to rate that for each root cause, and so now we have a severity rating for each effect, and a probability of occurrence for each root cause that could have produced that effect. Next, we're going to identify process controls and indicators. One example here would be brakes squealing. That's actually a design feature, believe it or not. It's not a bug. It's a way of indicating to the person driving the car that, hey, you need to change your brakes. And it gives you a couple thousand miles to do that and get that done. This is a way of mitigating the risk of your brakes not working at some point by annoying you to the point where you actually change them before they become a problem. So we're going to identify those process controls, those indicators, whether or not they exist. Sometimes you might have a design that doesn't have any indicators yet. This will help you hash out where those indicators need to go, because you're going to rate the detectability of each mode and or root cause. If you get different detectabilities for different situations, then you can rate them that way. But again, 1 to 10, where 10 is not very detectable at all, or you have no way of knowing what's going on, or a 1 where you are forced to pay attention to a warning, etc., like a lockout indicator or something like that. So next we're going to calculate what we call the risk priority number, the severity times the probability of occurrence times the detectability, and the criticality, the severity times the probability of occurrence. So if we have something that is really severe and really probable to occur, then whether or not we can detect that, that's a failure that we need to pay attention to and maybe mitigate in the design if we can. Because if it's both severe and probable, even if I know about it, I'd like to not experience it if we can get around that in the design. So it's something to pay attention to. So the criticality number is really important for identifying those failure modes and effects that cause either unsafe or undesirable conditions, whether or not we can detect them up front or beforehand and mitigate them that way. We want to try to mitigate that through the design and reduce those numbers if we can. Likewise, the risk priority tells us this failure mode or effect or root cause is much more severe, or we need to pay more attention to it than this one. It presents more risk, and hence the name risk priority number. Now, these aren't good numbers for an absolute comparison. What we want to do is use them to rate one failure mode versus another, and which ones should we prioritize and attack first, which ones have become kind of the most significant risks in our system. So this is a way of identifying that. And the last step is the most important step in this process. We use the design process to mitigate high risk or highly critical failures and reassess. We must reassess to ensure that the goals have been achieved. So what we want to do is we want to go through this process, steps 1 through 8 for our system. And you may have a bunch of different failure modes, each of which have a bunch of different effects and a bunch of different possible root causes. So this process can do a very good job of cataloging a very wide number of failure modes and effects. But what we need to do, the whole point of this exercise, steps 1 through 8, are completely pointless unless you do step 9. Step 9, we use the design process to mitigate high risk or highly critical failures. We get the risk priority number, we get the criticality number, then we go back to the design process and use it to solve these problems, reduce that severity, reduce that probability of occurrence, reduce that detectability number, get those better such that we mitigate that high risk or high critical failure and high criticality failure, and then we can reassess. If we don't reassess after the fact, we don't actually know if we made things better. So this is a way of guiding the design process to where it needs to go to mitigate risk. So let's do an example. We have 2 different possible failure modes. Here we've got a system, a battery, a switch, and the headlight on a car. And so we're designing a car right now. We've got one headlight. We'll just keep it simple. We'll say we've got one headlight. And we've got 3 components in the system, well 4 if you count the wires. And so we've got 2 possible failure modes based on what we're looking at here. And we're going to go, this is going to be very simplistic, so it's not going to be really in-depth. We could probably hash out a lot of different failure modes here. But these are the 2 major failure modes. Number 1, the light doesn't turn on, the headlight doesn't turn on when it's expected to. Number 2, the headlight doesn't turn off when it's expected to or when it needs to. So, possible consequences. For the first failure mode, we're just going to do one consequence for each one, that way, or effect for each one to keep it simple. So one effect of the light not turning on would be that the driver can't see obstacles, so the car would be inoperable at night. You can't drive in the dark without lights, especially out in the country. So that means that the car is operable during the day. This doesn't mitigate operation of the car for half of the day. So it's not complete failure of the system, but it is severely reduced utility. So you can't use the car at night, so it gets a severity number of 8. Possible consequence for the light not turning off when you expect it to, it kills the battery, and when the battery is dead, the car won't start. So the end effect is that your car is now completely useless. You can't start it, you can't drive it. So that would be a severity rating of 10, because it doesn't matter what time of day it is. If you don't have a battery, your car is useless. So let's list out some possible root causes. For the first failure mode, the light not turning on, dead battery could be one cause of that. in which case, so we would say that the probability of occurrence of this is an 8. It's probably going to happen at some point in the life of the car. You're going to wind up with a dead battery. It's fixable, but we're not addressing that here. What we're addressing is this going to happen? It's quite possible. It's not guaranteed to happen, but it's probable. A broken wire in the circuit somewhere. This isn't very probable. They do a very good job of guiding wires and putting them on members of the car's structure to protect them, and using different ways to protect the wires. So broken wires really don't happen very often in modern automotive design. So we're going to give that one a probability rating of 3. Headlight out. This is pretty much guaranteed to happen at some point when you're driving your car. So we've got our one headlight here, and it is guaranteed to die before the car does. They will. And so we're going to give that a probability rating of 10. Switch corroded. That's a possibility. You get some either galvanic corrosion, or maybe it was exposed to moisture or something. Switch corroded would have a probability occurrence of something like a 2. It really almost never happens, but it's possible. So it's not a 1. It doesn't never happen, but it very rarely happens. Or a broken switch, mechanically broken switch. Over time, if the car lives a long time, you might get a switch that you accidentally turned too far, etc. And so there's a low probability of that happening, perhaps a little bit higher than the switch corroding. But so here are 5 different root causes that could put you in the situation where the light won't turn on when we expect it to. Light doesn't turn off. So what are possible root causes of the light not turning off when you expect it to? Well, this one is a little bit simpler. There could be a short circuit in the switch. So somehow we got to close that circuit unexpectedly. So either the switch is malfunctioning in a way that keeps it on, in other words, a short circuit, or the operator error where you leave the headlight on when you don't mean to. So the short circuit, again, not very probable at all. Possible, but not very probable. So we give that a 2. Operator error. It's pretty common for people to accidentally leave their headlights on. And so not knowing anything else about the system, it's pretty probable that that would happen. So controls or indicators. What indicators do we have? Just in a holistic sense, before we look at anything else, we've designed this car from the ground up, and we've put one headlight on it because we're awesome and want one headlight for some reason. And the only indicator that we have right now that the light isn't on is that you notice that the lights are on when it's dark. So you can tell that the light is on or not if it's dark outside. If you're driving in the rain, perhaps not. According to Ohio law, whether or not you were aware of this, if your headlights, or if it's raining outside, you have to have your headlights on. But at any rate, if the light doesn't turn off, what indicators do we have there? Well, you would notice them that they're on in the dark, but if you've been driving with your headlights on during the day and get out of your car and park it, you're probably not going to notice that your lights are on. It's easy to walk by them because you don't see them easily during the day. So these are the only controls or indicators that we have right now. So the detectability here, if the light doesn't turn on, this failure mode, that the light doesn't turn on when expected, we notice that they're not on when we need them. So if we need them at night, then we're going to know whether or not they're on. But you don't notice that they are not on during the day. So there will be no way for you to tell if you're driving in the rain whether or not your lights are actually on. So we're going to give this a detectability rating of 6 because it's pretty moderate. And we're going to give the same detectability rating for the light not turning off when we expect because we have essentially the same controls and indicators and the same problems associated with them. You'll notice that the lights are on if it's dark outside, but you're not going to notice if it's light outside. So what we have here is a failure modes and effects analysis chart. It's not totally complete, but this kind of gives you the gist of what one ought to look like in kind of simplistic form. So we have the possible effect of the car being inoperable at night, and we've got different root causes that may have caused that situation, and then we've got the severity, probability of occurrence, detectability for this failure that we've determined before. And so we can calculate the risk priority number and the criticality and take a look at, in a relative sense, which failures do we need to focus on first, which ones are priorities. So for the possible effect, the car is inoperable at night. Let's look at the different root causes. Now, the root cause of the battery being dead actually increases our severity to a 10 for that particular case because the car is always inoperable. It's a complete breakdown of the system. You can't start the car if the battery is dead. So that one gets an increased severity. The rest of these are the severity of 8 that we determined for the car being inoperable at night, because you can drive it the rest of the time, but you can drive it during the day when it's light out, but you can't drive it at night. So it's very limited operability, but it is operable. And we see out of this calculation that we get the highest numbers here associated with the headlight going out and the battery being dead. And these are our two major failures that have a high risk priority number and high criticality. The difference being a risk priority number includes detectability in the calculation. Remember, the risk priority number tells us that this is both probable, severe, well, all three at the same time, severe, probable, and not very detectable. The criticality tells us, hey, even if this is detectable, even if we had a really good detection rating, if this is severe and probably going to happen, then we need to do something to try to mitigate that risk in the design. We need to be able to identify those things that even if I know that it's going to happen, I'd like to prevent it from happening if possible. So can we design around that? So we can use these two numbers to identify those root causes, those failure effects, those failure modes that give me large numbers that kind of need work in the design process, so to speak. So here we have a risk priority number of 480 for both of these and a criticality of 80. They have essentially the same end numbers, different ways of getting there. And so the question is, what can we do in the design to mitigate these risks and bring them in line with everything else? Well, let's take a look. So let's make two design changes. Let's use two headlights instead of one, and let's add a visual lights on display in the console so the driver has an indicator right in front of them telling them what's going on with their lighting system. So this first design change, using two headlights, adds redundancy, but the only root cause that it really helps out is this headlight being out. All of these other root causes could bypass that redundancy. Basically, the battery's dead, guess what? Both lights are out. A wire's broken in the circuit somewhere, probably both lights are going to be out. The switch is corroded, the switch is broken, there's only one switch for both lights, the light's going to be out. So it does help with the severity for this major failure mode here by saying, listen, we can drive it home with one headlight, as the wallflower said. So this reduces the severity number here by giving us some redundancy, but it doesn't really help these other effects. So we need to do something else to help those effects, either their severity or their probability of occurrence or the detectability. So the visual lights on display gives us a much better detectability rating. It really reduces that detectability number because you can see, are my headlights on during the day? Is this causing me a problem? Can I drive during the rainstorm in a legal fashion, in Ohio? So the detectability has greatly improved. Now, notice we've got this greatly improved detectability number, but the criticality is still pretty high for the battery being dead, certainly, and the headlight being out. The criticality is also still high because the probability of occurrence is very high. So if we wanted to further improve these numbers, we've gone back, made a design change, recalculated. We see that probably we still need to do something to mitigate the battery becoming dead. What do we want to do? Could we reduce the probability of occurrence of that? The severity, probably you can't change with the battery being dead. That's just the way it is. It's a critical component, hence the name criticality. It's a critical component in the system. So we could reduce maybe the probability of occurrence with a further design change. Feature commonly found today in cars is that the headlights automatically shut off if you've been away from the car for a certain amount of time. So making those systems automated could reduce that probability of occurrence of killing the battery because you left the lights on or whatever. Regular service, better battery design, etc. It might change these numbers. But we can see that we made a change, went back and recalculated, and we've improved the system, certainly reduced the risk priority number for both of these failures. So let's look at another failure mode. The light doesn't turn off. We've got a possible effect here for this failure mode. And there are probably many more, but let's just look at this one. The car won't start as a possible effect because we killed the battery. So we killed the battery. The root cause in one case might have been a short circuit in the switch, and in another case might have been operator error. In both cases, the severity is 10. You have rendered the car inoperable. And so there's really not a good way to mitigate that without mitigating the probability for these events to occur or the detectability. So operator error, unless we train better operators, that probability of occurrence is probably going to stay pretty high. the probability of a short circuit in the switch is pretty low. So we see a risk priority number here of 140, criticality of 20. So it's not very probable. It's really severe, but it's really not very probable. Whereas the second failure has a risk priority number of 560. That's pretty darn high. So, and a criticality of 80, again, we have a high probability of occurrence, high severity. So this is one of those failures that we really need to pay attention to. So let's make a design change. Let's add an audible indicator when the driver's door is opened, so that if you try to get out of the car and the lights are still on, it beeps at you this really annoying noise that's going to tell you, hey, your headlights are on. And let's also add a visual lights on display in the console. We did that actually associated with the other failure mode, but we're going to get benefits of it here in terms of detectability. So again, we're going to get that good detectability rating. We're going to reduce that detectability rating down to a 2 because we have a lot of different ways we're stimulating your ears, your eyes, etc. to tell you, hey, the lights are not on. Or I'm sorry, the lights are still on. And so we see that we've reduced the risk priority number to 160. We can't really change the severity of the failure here unless we really fundamentally change the way that the system works. We can't make a dead battery not a severe failure. We can reduce the probability of occurrence if we did something with, say, the driver, so in terms of operator error, training them, etc. And maybe that would be an effect over time of this indication system, but right now we've improved the detectability number and we've brought that risk priority number down from 560 to 160. So we've greatly improved it. We can call this a good design change for safety and reliability. So we've seen how failure modes and effects analysis can help us categorize failure, identify it, and then sort out which failure modes need attention in the design process and verifies that our design process has actually made things better. So it's a really useful tool. It's very easy to use, and it's great for documentation. I highly recommend that you use this tool wherever possible in the design process to help inform your decision making, because it is very easy to use and it gives you a really good picture of where you might encounter failure.